All right, here we are at our last organometallic reagent of chapter 20, and it's called organocuprates. Cuprates have copper, that's the cup, because copper is Cu on the periodic table. So how do we synthesize them? It turns out that we just take organolithiates, or lithium, and treat those with copper iodide, and instead of it being kind of one metal with one alkyl part, it turns out that cuprates actually form two bonds to the copper. So it's kind of dimers of those R groups. Just kind of thinking back, how would we synthesize an organocuprate? We need the organolithiate first. How did we make that? We made that from an alkyl halide, mixing that with lithium metal. So we've already learned about organolithiates and Grignard reagents, and we said essentially that those two things have pretty much identical reactivity. So why are we learning about this third type? And it really has to do with the reactivity of this species. So if we think about the copper-carbon bond, the carbon-copper bond, is it going to be more or less polarized compared to other organometallic reagents? And you probably don't have a periodic table, but how would you figure that out? You just look at the periodic table and say, oh, what is the electronegativity values of these? And I brought one right here, and what we essentially have is carbon over here, and lithium and magnesium are way over here. So difference in electronegativity between the two sides of the table are really, really far apart. What about copper? Copper is a lot closer to carbon, right? So it is a lot more electronegative of an atom. So it turns out that the copper-carbon bond in these cuprates is less polarized compared to the other RM reagents, the other organometallic reagents. So what about this blank? Cuprates are blank reactive compared to other organometallic reagents. Well, one kind of theme of this chapter has been the more reactive reagent generally tends to have a more polarized bond. So cuprates are less polarized, so that means that they would be less reactive compared to other organometallic reagents. So I left a blank right there to kind of correspond to how does that reactivity difference really impact things with organometallics. So what if we had an aldehyde? So let's just look at this aldehyde. It's called acetaldehyde, ACET, acetaldehyde. And what if we treated that with a cuprate reagent? So just to remind you guys, if we were to take this and treat it with an organolithiate, what would happen? The organic part would add to the carbonyl, and we would generate the alkoxide with the newly added R group. This alkoxide would then protonate if we added water to the reaction. And this is the more reactive lithiates. So what happens when we have cuprates? It turns out that when we have just aldehydes, so RCHO would be an aldehyde, RCOR, ketones, esters, amides. If we treat any of those reagents, any of those starting materials with cuprates, we actually get no reaction. So I'm going to put a big NR, no reaction with that. And that's because they're less reactive. It turns out that there will be a functional group that they do react with, and I'm getting to that in a minute. But essentially, the last thing to fill in here is that organocuprates show no reactivity, no reaction. So we'll put no reaction with all those other functional groups. It's going to require something else for that cuprate to react with a starting material. So, that's a pretty good segue. I wonder what is going to react with the cuprates. Maybe you'll find out soon. You're back! So, it turns out that organocuprates react with something called alpha-beta unsaturated carbonyls. So let's break that down a little bit. So what's a carbonyl? That's just C, the double bond O. And then what does it mean to be unsaturated? If we had just a 6-carbon chain with no double bonds or rings, that would be an unsaturated alkane. if we just put a double bond in there, now that has 1 degree of unsaturation. So it turns out that unsaturation just means having double bonds. I think a lot of you probably knew that, but it's always good to review. So what does it mean if it's alpha beta unsaturated? Well, what does alpha and beta mean? So again, alpha beta refers to positions away from the functional group. So if this ketone is our functional group, that's our carbonyl, this would be the alpha position, this would be the beta position. And not that we need to go any further, but this would technically be the gamma and the delta position. So alpha beta unsaturated carbonyls are molecules that, and this would be an alpha beta unsaturated ketone that I just drew up there. So they have a double bond or a triple bond essentially between the alpha and the beta positions with regards to where the ketone is, or the aldehyde, or the amide, or the ester. So really it can be any of those functional groups as long as we have that alpha beta unsaturation. So what I want you to do actually is just take a minute and think, we just learned that cuprates don't add to that carbon. We said they have no reaction with that. So where are they going to add in this system, in this alpha beta unsaturated carbonyl compound? And it might help you to try and draw all the resonance structures possible with that. And one of them is likely going to be to allow you to identify where the electrophilic position is. And remember, what is an electrophile? It's a partially positive charge. So pause the video and do that, and then come on back. Okay, good job. You already identified it, but let's talk about it together now. So we could imagine one resonance structure being where we pull those electrons up to the oxygen. That would make the compound look like this. And additionally, if we want to further show where the charges are delocalized, this pi bond here can move over there. When it does that, we would have this reactivity right there, or this distribution of charges right there. So we already explained how alpha beta unsaturated, or how organocuprates don't add to the carbonyl carbons. So this resonance structure must not show us anything about how that works. But where else is electrophilic? Also, the beta carbon is electrophilic. So this is an electrophilic carbon. So if we have specialized nucleophiles like organocuprates, they could theoretically add to that partially positive position. So that allows us to essentially decide how we want to react these alpha beta unsaturated carbonyls. So if we had this molecule, so I'll just draw this molecule, and we decided we want to add another methyl group to that position right there. How would we do that? The first thing we would do is either add an organolithiate or a Grignard reagent. So we'll just do the lithiate because it's slightly less to draw. So CH3 lithium, that would add to this position there. And secondly, we would quench that solution with a little bit of slightly acidic water, and that would provide us with the alcohol product. And this new CH3 was added from that reagent right there. So we have some organometallic reagents that allow us to add directly to the carbonyl carbon, but the cuprates are specific for adding to that beta position. So if instead we were like, oh, we actually want a carbon linked to there, we just have to take our organocuprate, add that instead. So we'll show the mechanism of that too. So essentially, if we were hoping to make this molecule here, we're adding a CH3 there, we would need to add the organocuprate. So one would be CH3. There are two of them. There's copper lithium. And essentially, the organolithiate, I'm going to redraw it right here with the lithium, would take the electrons in that copper carbon bond and add them to that electrophilic carbon. When that adds there, this bond has to break, right? Because we would have too many bonds to that carbon if it doesn't. So that's going to shift over here. and this is going to shift up there. That produces the product, or the intermediate, that would look like this here. And at this point, it's clear that the negative charge, the electron density, is on that oxygen, but it's also on the carbon right there. So we can draw that as a secondary structure. And essentially, after we add the cuprate, we need to work up the reaction with some water. So we'll say it's slightly acidic water, H3O+. So we have some H+ around. Those electrons are just going to go grab that, and that produces our product. So that's the power of multiple types of organometallic reagents. Some of them add, how we would say, we would call this just directly to the carbonyl carbon, and the other ones add to the beta position, which we often call conjugate addition, because technically in the starting material, those pi bonds are conjugated, so we call it conjugate addition to alpha-beta unsaturated carbonyls. So that is the power of these cuprates, and please let me know if you have any questions. Yeah.